Hello everyone, this is group 227 for the AspenTech competition, and this is our project. In this project, we'll be tackling corn biomass waste transformation into useful products. Corn waste gasification for methanol and iButane production offers a promising solution. It tackles waste management by transforming what was once discarded into valuable resources. This approach promotes sustainability in several ways. First, it reduces the reliance on landfills. Second, it's a renewable fuel production. And thirdly, it promotes circular economy. Here's an image of the process that we'll be tackling today. The first part is syngas production. The second part is methanol and iButane formation. The last part will be the separation of methanol and iButane and their storage. So now we're going to tackle first the syngas production. So first we started by specifying the non-conventional solid that we have, which is biomass, at 700 degrees C and 1 atmosphere, and we introduced it at 5,000 kilograms per hour. Also, we used the proxanal in order to specify the breakdown of the solid into moisture, volatile matter, fixed carbon, and ash. Altanal was used in order to specify the elemental composition in weight percentage of carbon, hydrogen, nitrogen, oxygen, and sulfur. And for the sulfonal, it was used in order to specify the sulfur content in the solid. Firstly, the corn stover is collected and fed into a decomposition unit. Its purpose is to remove the moisture from the wet biomass. The dried biomass is thermally decomposed in a pyrolysis reactor and, in absence of oxygen, to produce carbon monoxide, carbon dioxide, and methane. Nitrogen was also added into the system so we can add inerts in the reactor. A splitter is then employed next in order to separate the gases from the solids. The solids, which are mainly composed of carbon and ash, were also separated. Carbon, the effluent gases from the splitter, were combined with steam and air, which are the gasifying agent, in order to be introduced into the PFR.
The gases, mainly methane, undergo steam reforming to produce hydrogen and CO, in other words, syngas. The products are then fed into a second PFR, where the gases undergo water-gas shift, methane dry reforming, among other reactions to produce more syngas. The gasification process converts the syngas into a richer H2 and CO mixture, which are the essential elements in producing methanol and hydrocarbons. The reactions and kinetics of the oxidation and reduction reactions are found here. And now for the methanol and isobutane formation. The previously produced syngas was then cleaned from any impurities that might interact in the catalyst in the methanol synthesis reaction. Then, water which was pumped to 60 bars is mixed with clean syngas which was compressed to 60 bars. This mixture was then cooled to 280 degrees Celsius and fed into the PFR to produce methanol. The catalytic reaction was introduced to the PFR based on the Longmire-Hinchinwood method, which had the following great expression and the following constants.
After the methanol formation, we proceeded with the formation of isobutane. The rest of the syngas is separated from the methanol and is fed to another PFR for further reaction in order to consume all the remaining hydrogen and produce hydrocarbons, mainly isobutane. The fuel synthesis reactor is based on the Power law method, and these are the reactions and kinetics needed for the hydrocarbons formation. And for the last step, we have the separation of products and storage. Using a flash separator, the water which is in abundance in the stream was separated from the rest of the gases. These were further split into an upper stream containing flue gases and a downstream of hydrocarbons which mainly include the isobutane. The separated methanol stream was also cooled from the gas to a liquid phase to be stored at 20 degrees Celsius. As a summary of our results, 5 tons per hour of corn stover were converted into useful products as isobutane, methanol, and biochar. To conclude, we have successfully transformed biomass into useful products through a series of reactions followed by the separation of products. In order to put this technology into action, we need to conduct economic feasibility analysis and life cycle assessments to understand its environmental impact. This involves conducting case studies and pilot-scale experiments to optimize yield and to confirm the accuracy of simulation predictions. And these are the references that we used in order to input the data in the simulation.